So, welcome to my talk. I will give you a deep dive behind the curtain of standard function. So, let's start with some words about me. So, in case you cannot compare, that's me. I'm Andreas Reischuck, and on the internet you can find me as ArpMind everywhere, on GitHub, Twitter, and so on. Feel free to contact me. I give online presentations, trainings, on-site trainings about C++, Qt. Clean code is one of my favorite topics. So you can also hire our company. We will help you write software projects. And on the other hand, we are also always hiring. So if you have interest in doing deep level C++, a lot of open source projects, then you're welcome. Yeah, so that's what I said. Work for us. Just a disclaimer in the beginning, like almost everyone, even though I give lectures, I'm also just learning. Nobody is considered an expert in C++. It's just moving too fast. And yeah, so let's go then. Before we start with a deep dive, we should level everybody up, get on the same page. So start way on your surface, and then we go deep, really deep, I hope. So goal is that everybody, even an expert, should learn something here. So let's start with a simple C++ function. I hope everybody agrees that's the simplest C++ function we can write. No return type, just a name. And first thing I want to mention here is the training return type. Comes from the lambda syntax. And in all my trainings, I find there are some developers who don't know it. And those functions are equivalent. So it's the same return type, there's nothing magically here, just the return type is on the right side and not in the beginning. So, next thing, function signatures are types in C++. And for example, if you write this, that's a type alias called void function, which is just another name for the type of the function signature of the void function, returning nothing. And the training return type, of course, also works here. So you can write it the same. So no matter how we write our functions, if we leave out the function name and the implementation, of course, then we get a signature, and the signature is a type, just like a normal type. But it's not like your regular int or something. Because what's the size of our type here? Anybody knows? No, it does not depend. There is no type, no size. So, and it's like void. Void also has no size. And the function itself, the signature, this type has no size, like void. And like void, the only useful thing we can do with that is create a pointer from that. So that's the next thing. So we can create a pointer. And then, of course, we want to use it. And void pointer has nothing to do, but our function type has a thing to do. You can call the function. So first, we can declare variables where we say, okay, our normal function, this is just a void function, can be assigned. So we take the reference, the address of the function, and assign it to our pointer. And then we can call it, just like that. So any questions so far, or is it clear for everyone? So next step. The function pointer of a function is always const expr. So it doesn't matter if the function itself is const expr. That means the function is executable at compile time. But the pointer to the function is always const expr. We can always write this. The interesting twist about it is, how does the compiler know at compile time which address the function has? I cannot know. In modern operating systems, the address of the function is only known at runtime, because we have address randomization, so the function is loaded anywhere in the RAM. We cannot know before. But how can the compiler pretend to know it? Yeah, it just does that. It pretends to know it. There is no address. And that's also why we cannot, in extra context, access the actual addresses. The compiler does not allow it. We cannot print it or convert it to a number or something, because the compiler doesn't know. He doesn't know where the variables live, and he also doesn't know where the functions live. So, but it pretends to know it, and tries to keep that illusion alive. Okay, and the context to a function pointer can also be called. So, yeah, let's summarize it up. So, function signatures are types. That's the first point. Second, we can store pointers to functions. That's the only thing we can store from functions. And function pointers are known at compile time. So far, all basic C++, I hope. Any questions? None? Great. Then let's continue. First question is always, why would you use standard function anyways? What's the reason? And I want to use this opportunity to also introduce you constructs we use later to implement standard function. And let's start with a good example. Where would you use standard function? And the first thing would be like in a callback. So we have, for example, a button. The user clicks the button, and we want to trigger some action. But the button class doesn't know which action you want to introduce. So you can give a button a different label, like OK or cancel, and then you want to do different stuff, depending also on the dialogue, what is happening. So how do we do that? So first thing, we just learned function pointers. Let's try that, function pointers. So some code. I won't show you all the button details, only the important parts for us. So we have a button, and this button has to somehow call back something. So we can call function pointers, so let's store a function pointer, and then let's try to use that and write an edit dialog. And the edit dialog has an OK button and a cancel button. And yeah, we have two functions then in the dialog, one who should handle the OK case and one for the cancel case. But how can we get this called? These are member functions here, and so we have to know which dialog the function has to be called in. So the button only has one pointer. I can just call the function, not a member function. That won't work. So next challenge then is we have to somehow call the instance method of the dialog instead of just a global method or global function. And we say, okay, we only know normal C++, then the only thing we can do about it is to have a void pointer, because we don't know which dialog is implementing the button or is using the button. Could be just a file dialog, could be a different dialog, should be a print dialog, for example, different classes. So we don't know anything about it, it's just a void pointer. Void pointer is bad, but yeah, let's look how it works. So we have an instance pointer now in the button, and also the function pointer, which uses the instance then to call it. And yeah, it seems this leads nowhere. Because we can do that, but having no types, no type safety is probably bad. So we have an extra pointer, but it's C-style. Yeah, I don't know if I would recommend it. Try to avoid it if you can. So, any other idea how to do that? First thing that comes in mind, let's use an object-oriented approach. So, what I mean, we can create a simple interface and say, okay, you have to implement this interface, and the button is just keeping a pointer to this interface, and then we can call the virtual function. First gotcha here is, in C++, we always have to do a virtual destructor here in the interface. Otherwise, it's simply too easy to create undefined behavior interesting ways. So then let's try to use that. So we have an edit dialog again with 2 buttons. And then we scratch our heads. How should we implement an interface here? We have 2 buttons, 1 dialog. So dialog can only implement 1 interface, not 2 of the same kind. So we would have to have new subclasses just for handling the button case. That also becomes really awkward and is not really feasible. So object-oriented approach, yeah. We have this clickable interface, but yeah, got nowhere. No real implementation that we would want to use, I would say. So I think the solution is obvious, isn't it? It's the elephant in the room. We should use standard function for that. That's why I'm talking about this topic in the first place. So let's see how it's used in this case. So first we include the necessary header. So we have the functional header where standard function is defined. We say, okay, our callback is an instance of the function template with the type signature. So we don't expect to return anything, so it's just a simple void function. And then the button just has an instance of this function template instance. And the edit dialog now can simply implement the constructor, and we can say, okay, in the OK button, we assign a lambda to our clicked handler in the button. And that's the main 90% use case for standard function, I would say. So, easy solution, use standard function. It's type safe, it's easy, nice. Any questions so far?
To play devil's advocate here for the OOP approach, in this specific use case, couldn't I just have used a pointer to a member function with an interface? I mean, I wouldn't do that myself, but because here we have quite well-defined lifetimes and don't need the genericity at the moment.
Yeah, you can always make it work, I would say. Yeah. And if you can make it work for your use case, then it's okay. But I would say you jump extra loops anyway to get it working. And standard function is simpler and more safe, because now you have to, as you said, define, okay, my destruction sequence is always known and so on. So in standard function, you don't care, it just works or not. Yeah, other questions? Okay. But this is not the only use case for standard function. There are different use cases. So this use case, we always have something like one pointer where we want to call our function handler. So a member function somewhere else. And it's, as I said, like 90% of all instances of standard function are this simple. But there are more complex instances and use cases for standard function. And one extreme example is a task scheduler. So like in the morning keynote from Daniela, we have an async task scheduler somewhere in the background, and she scheduled some various tasks like handling network connections and so on. So let's sketch that also. So we have a generic scheduler, and the scheduler is supposed to schedule a task. I named it queue up a task, and then it's supposed to later run this task on some thread at some time when it's appropriate. How do we find the task here? And the simplest implementation for that is simply use a standard function. Because the scheduler itself doesn't care what this function does. It only has to capture it once when you queue it up, and later has to execute it. And all the parameters that the task would want to work on and so on, it should capture by itself. And then, for example, we have just a queue where we queue up all the tasks, and then later we have a thread somewhere who's requesting, is there a task for me, give me that, and I execute it on the thread here. And For example, if you have think about an image processor, then the whole image would be captured in this function. So it's not just one pointer to some member function in a class, but it's the whole object that can be captured here. And the scheduler doesn't care. You might have a pointer, you might have an array or a vector, doesn't care how big your object is, it's always working. So in this case, you have much bigger objects you want to hide in the standard function, not just one pointer. So to sum it up a bit, a standard function can store any callable, no matter if it's small, like one pointer, or big, like whole image. It's always type safe, and yeah, most use cases are small callables. So we should optimize for the small, or for the most often used use case, and then also make it work for the task scheduler use case. So any questions so far on these examples?
I'd like to nitpick on the type safety. Yeah. As far as I know, std function still does not care about the constantness of like a member function. So that's one in the function ref paper, that's one of the changes they make to the semantics of std function besides the ref part.
There are problems, of course. Yeah. But the use case works, and it's more type safe than having void pointers everywhere. So now that we know how standard function works, what C++ constructs are, then let's go and deep dive behind the curtain. How does standard function do that thing? And I want to introduce you by just writing a new implementation of it. So we now have seen the use cases, so this is our goal then. And we want to write a naive implementation that works for the use cases we described so far. And so let's start with that. So first thing, we somehow have to support the use case where we say, okay, we have a function, this is a template, and we have a signature. How do we get this thing to work then? So we create a template. We have the strange angular bracket there. And what goes in this comment here? Exactly. Function signatures are types, so it's just a type. Because like any other template, it's just a type, can be a signature. But how do we access the arguments in the return value now? So we somehow have to know which types are the arguments, what's the return type of the signature. And the thing we used for that is partial template specialization. So what we do here is we say, in the first thing, we say, okay, there is a struct named function, and this is a template. And it's templated by one type argument. And now we say, we have no implementation for that. We don't know how to implement function for any type, but we know how to implement function for a function signature. And this kind of pattern matching is supported by the C++ compiler. And it says, okay, if this type we give to the template is a function signature, so it has a structure like a return type and then a lot of arguments, then we have an implementation. So that's the first trick to get this working. And now we already have in our specialization the return type and all the arguments. And now we have just to implement it. So first thing we have to do, we want to somehow call an instance of this function. And for that, we can use the call operator from C++. So it's just the operator keyword and then round brackets, and this is the function name. And then we have another round brackets for the arguments. And what goes there in the question marks? Any ideas? Yeah, go ahead.
Well, the arguments and the return type, obviously.
Yeah, from the template signature, basically. So let's add that. And it's actually that simple. And what's the implementation now? We don't know, but we have the call operator at least. And actually, we cannot know. How would we implement that? We can only implement that through some other mechanism. So let's pretend we have somehow stored a pointer, and then we can call a method on that call, and just forward all the arguments, and the return type is returned from our call operator. And yeah, how to get this kind of API working? Let's try again the object-oriented approach and pretend we have an interface for that. So we write a call interface and then have a call member method. And the only thing we have left to store is the pointer. And to make it easy, we store a shared pointer. So we don't have to think about how the lifetime is managed, just to get it working here. So far, everybody can follow. So we have now an mptr as a member, and we can call the interface with that. So what's now left is to implement that. So the implementation has to be templated again by a concrete callable. So that's different. That's not the signature of the function, but this is a concrete callable like a lambda type we cannot name otherwise. And this call impl now has to implement the interface. So we derive and say this is the final implementation. And to make it work, we store the callable as a member and override the call. And what do you do here? Yeah, we just call our callable. So in the simplest case, our callable could be a function pointer. And this would work, but we can expand a bit very easily. There's a construct, like a standard invoke. And if you use that instead of the call operator directly, we get some features for our function implementation extra. We inspect that later. So what is missing then? We have to somehow create a call impl somewhere. So what do we do for that? We have to write a constructor for our function. And this constructor has a strange thing that it is templated again. So we have a template function, and we have inside a constructor that is also templated. But this time, again, with a concrete callable. And now we have to be a bit careful here, because we say this is template, and this template would match any type. Compiler doesn't know or care about the names we give it. So callable could be our function object itself, and then this would be a copy constructor. But we don't want that. And if you don't want that, we say in a requires clause, just callable should better not be a function. So if it's not a function, then this constructor is callable. If it is a function, then we use the copy constructor from the regular C++. Okay, and then all that's left is initialize our member pointer by constructing a new instance of the implementation and give it our callable. And to make that work, we also have to give our call implementation a constructor that also just stores the callable. Yeah. And strangely enough, after only 4 slides, this is it. It's the implementation of a very basic function. And that's all the code we had. I also sneezed in some blank lines here, but I cheated and put all the code on one line. Any questions about our naive function implementation so far? In the back? Yeah. Wait for the mic.
So does this also now handle member functions?
Yes, because we use invoke.
Because of invoke?
Yeah.
Okay, thanks.
So, but we will see later how this feature actually works. So I will give some slides for that.
Why do we need child pointer here? Why don't we use unique pointer, for example? What do we share?
We start sharing once we clone our function instances. So if we have two of them, then we only have one object constructed, and both point to the same object. So that's why we share. And to work around this, we could use unique pointer, but then we had to somehow implement a clone function to get copyable function objects. And to make it simple, this code is shorter without unique pointer. That's the reason. And also a unique pointer wouldn't help us that much. So why bother? And always the first goal is to get our API working. And that's what I want to show here. So we had some use cases and we said, let's implement only the code that is necessary to get it working. And if you want to implement yourself, it's already difficult enough, so let's not bother with unique pointer. You can always do that later. Here in front.
But hang on, if I understand this right, this now has very different semantics from stat function. Because if you copy a stat function, it's going to copy the underlying object, whereas this is going to just share it.
Exactly.
So that's actually different from stat function now.
Probably, because we just did a naive implementation.
Okay.
So
Just checking if I understood what you were doing.
yeah, we go deeper. So this is only the beginning here. Okay, if there are no questions, then let's summarize it again. So what have we done? We have used partial template specification to get one implementation of the function going. We have the call interface and a shared pointer to the call interface. And a templated implementation of this interface, so everything works together now. And there was already the question now about the standard function interface. So the question now is, what is defined in the standard that we do not yet have implemented correctly? So let's compare what we have already. And one thing we have, we got the template signature right. We didn't intend that, but that's the same as in the standard function. And next thing, there's a standard mandate that store, copy, and invoke any callable can be consumed by our function implementation. We also have that. And we have the call operator. So far, these are the only 3 points we have, but there are a lot of points we don't have. Let's investigate. So first thing that comes to mind is the empty state. We didn't bother to think about what is the default constructed function containing. And the standard gives it a name, it calls it empty state. So if there is no function stored in a function object, then this is empty. And it calls, when we try to call such a function, then there should be a bad function call exception thrown. So throwing exceptions is a bit debatable, but that's how the standard mandates it. And with this empty state, there are also some APIs that come with that. First thing is, we can check if a function is empty. That should be possible to prevent calling an empty function, if it's always an exception. So we have an operator bool. Now, to extend that to our implementation, that's very easy. We just check if our pointer points to something. So if it's not initialized, then it's a null pointer. So we can easily check that. Next thing is, the standard mandates that there are constructors for the null pointer overloads. So when we construct our function with a null pointer, then we should construct it with an empty state. So it's explicit. We say, okay, assign a null pointer. It's empty. So in this case, in this constructor, we don't have to do anything because our pointer, our member pointer is already a null pointer by default. And we can also assign null pointer. In this case is a bit more involved. We have to reset our pointer to ensure that it's already a null pointer, and then return our this. So far, not a big problem. The only use case that is left here is, I won't implement that, is raising exception if you try to call it with an empty state, because I don't like it. And also throwing exceptions is easy. And we don't need that now. And there are more interfaces for that, so we can also compare for a null pointer now. So we compare a function instance object with a null pointer. And normally you would have to write more combinations of that. So you can compare a left null pointer, on the right side a function object, and also this way. But we don't have to do that, because in C++20, if we just implement one of them, all the remaining parts are implemented by the compiler for us. That's also the reason why we would use a free comparison operator here. And the implementation is also kind of easy. You just have to check if it's the bool operator overloads it to true or not. So that's all about the empty state. And then the standard also mandates an interface for swapping. And this is also kind of curious. Normally I wouldn't write it that way, but let's look into it. The first thing is we have a member function swap that gets one argument, that's the other function. And we are supposed to swap the this function with the other one. And the implementation is just calling standard swap. So the member function calls the global standard swap function. And now we have also to implement or overload the standard swap function and implement that. And we implemented with swapping the pointers. Yeah. So the member function does the actual swapping, and the global overload calls just the member function. So why we need the member function, I don't know. But that's what is defined for standard function. Okay, next thing, we also have to have some types. It's also kind of interesting. Now, in C++20, the only thing we have to provide is a result type. And that's our return type, basically, of the function. All the remaining parts, there were a lot of types defined. They are no longer necessary for implementation. So we skip that because we don't need it. And it seems like the function API was somehow created in a rush, and everything that was needed or deemed needed was put into it. But later, someone said, yeah, we don't need it, let's remove it. So now we come to this strange thing with the member pointers. So our function object should be able to handle member pointers to functions and data members. Has anybody used this kind of feature? 1, 2, nice. 3, 4, 5, not bad. I have never used it before, so I was kind of surprised to find this feature. So let's explain how this works. So we implement or include our functional header, and then we have a class or a struct to make it shorter. Then I don't have to write public and such stuff. That has a data member. And now we have a function signature from the standard function that expects a pointer to this object and returns the member value, the int. And if we have an instance of this struct, we can create an instance of our function. So it's an instance of a standard function. We construct it with the member pointer to the data member. So it's not an actual data pointer. It's just, if you have a struct, then extract me the member data. And then we can call our data func simply by calling it with a pointer to our example. And that's the member data, and let's also look how member functions work. So we change the data member with a member function here, and then we can do the same and invoke it the same. So our function also abstract about data member or data member function in this case. And as I said, I never had a use case for that. So I think you have to expect that, have to know this feature, and then also say, okay, let's use it here. And so far, it never happened to me. But there are more strange features in standard function. And one of the more strange ones is the target type. So standard mandates, we have a member function or a standard function, target type, and it should return a type info object. So that's the RTTI information about the object we stored, the callable. And then there are two functions to extract this object. So you, as a user, have to provide a concrete type, and once this type matches to our callable, we get a pointer back to the callable. Has anybody used that feature so far? One. Ah, cool. And I think it's a very, very strange feature, and I would think 99% of all usages of standard function will never invoke this method. But we have to pay because the runtime type information for all the types we put in the callable has to be stored in the program. Because we cannot know if this function is invoked or not. And it's a virtual interface, so yeah, we have to make this work, it's a lot of hoops we have to jump. And yeah, if you don't use it, why do we pay for that? So that's all I have. So let's summarize a bit. So we had this empty state. That's what kind of easy to implement. Bit of a strange tweak with the null pointer. I don't know if this is actually necessary, but yeah, it's okay. Can live with that. Just another API. Then there's a bit strange swap implementation, but we need swap anyways, so having an extra function is not a big deal. And then we start to get somewhat questionable with a member pointer, but we've seen some people use it, so it's also not like we have to do a lot of stuff to do it, just standard invoke, and it's implemented. We already have that. And then there's a strange target type feature that seems nobody's using, and it's still in the standard. Yeah. Any questions on this so far? Am I missing something? Yeah.
Sorry, just a quick comment, because you mentioned these argument type, first argument type, second argument type things, and you said something about we didn't get the interface right in the beginning or something. Just wanted to clarify. Yeah. They were there because we needed them for support of the old C++98 binders, std bind first and std bind second, and std not one. And we removed all of those things because you're not supposed to use them anymore because lambdas are much better. And so we removed those, and then we didn't need those types either because they were to support these other things that we removed. Yeah. So that's why they were there, and that's why we removed them. Just FYI.
Yeah, so it's not a mistake in the beginning because it was needed for compatibility, but now we have deprecated the use case, and now we don't need it anymore.
We have removed the use case. You have deprecated it in 17, and we have removed it in 20. And that's a good thing. We don't need that anymore. That was kind of broken anyway.
Okay, great for the insight. Thank you. Anyone else? Are we missing something?
Maybe a small comment about target type. It could be used for partially comparison functions because std function doesn't really support comparison. And sometimes target type can be used for this.
Okay. things. So we have at least one use case, but I would still argue that 99% never will use it, because most of the standard function usages will never be sorted or partially sorted. So, yeah. But we are missing one big thing. So the standard mandates or recommends, which is the same in practice, that we should avoid dynamic allocations. And that's the thing we always do with the shared pointer. We always allocate. And it also describes that we should, for callable that only holds a pointer and a member function pointer, should not allocate. And I was a bit confused by that. What or and combines here. And yeah, so let's look how in practice the standard libraries implement that, because that's a feature we can easily observe. And also, let's compare the standard libraries, how they do on the remaining features. And yeah, let's go for comparison here. What other implementations did I look at? So the first one is the Microsoft STL. It's open source now, so we can look in all the code. We have the GCC standard library, the libc standard C++. We have the LVM project. They also have a libc++ replacement library. Curiously, standard function is like the first value object. They implemented API incompatible to each other for some reason. I don't know. I would guess that libc was first, and then GCC was not in the mood to copy that, and so they created their own, and now they're incompatible. But it's just my assumption. I don't know anybody and spoke to nobody. Then there's the Facebook Folly library. They come with a function implementation. And then I found an interesting function implementation, the function2 library. I would guess nobody uses it because I couldn't find many comments about it. But they implement a lot of extensions that go far beyond what is in the standard right now. We will have a look later. So we want to go fast, I guess. But I have to tell you, I won't provide any benchmarks here, because these benchmarks are highly dependent on your use case. So if you have a large function, for example, that takes a lot of time to process, your standard function overhead doesn't matter. But if you have a small function, then it will matter. And how much it matters depends on your use case. And also the compiler will do different optimizations. So many compilers now know how standard function is implemented, they know how it works, and they will try very hard to optimize that. That's my assumption, because for standard function, they do optimizations they don't do for other stuff. And so it would depend on your use case if those optimizations are taken care of the compiler or not. So making benchmarks here is almost useless. And the benchmarks I found online also suggest that there's basically the same for basic benchmarks. There's not a big difference between them. And what kind of benchmarks would you want for your applications? So one thing is, for example, how long does a call take? But that's only part of the equation, because you have also to construct these function instances and also destruct them. And depending on your use case, you will also copy them or move them around and so on. And how much time it takes will depend on your use case and how you combine these features, what is most often used by yourself. So measure your use case and don't rely on any benchmarks in the presentation, and I won't provide anyone. So, yeah. But there's a different benchmark that always counts, and that's the size. So that's the low-hanging fruit, and like the hummingbird, the smaller you get, the faster you can act. And that's the same for standard function implementation. And we have seen in the C comparison that we need 2 pointers, one a void pointer and then a function pointer. And if we set our benchmarks, then we know what to compare it to. So let's see how our standard libraries compare to that. So Microsoft, yeah, big numbers here. So let me explain a bit. So I counted pointers. So depending on your system bits, a pointer has a different size. On 64 bits, a pointer is 8 bytes. On 32 bits, it's 4 bytes. But using pointers makes it comparable between platforms. And Microsoft decided, for example, to have something like 6 pointers plus 16 bytes, for whatever reason. So this always computes to the total size. And these two numbers here are, you have 8 bytes for your function object itself. So that's a small memory buffer. And there's 2 pointers overhead. So 8 pointers in 32 bits are for your function callable. And 2 pointers are overhead for the function implementation itself. So once you go beyond 8 pointers in 32 bits, you will have to allocate memory on the heap. That's the whole thing. And the total size is then 10 pointers. And in 64 bits, it's 6 pointers and 2 pointers for overhead. So the GNU library always has 2 pointers for your callable and 2 pointers overhead. libc++, it's a bit more strange. They have, I couldn't find any compiler that could compile 32 bits. That's why I don't know it. And on 64 bits, it's 2 pointers for your callable and 4 pointer overhead. So kind of massive. Folly is more like Microsoft. It's like always 8 pointers. And function 2, actually function 2 you can provide traits, how big your small memory buffer should be, but the default is like 32 bytes all the time. That's why the numbers differ a lot between the platforms. And if you look at the whole chart, then we will realize it's always more than 2 pointers. So I would say, okay, 2 pointers should be enough. Why do we have like 10 pointers, 8 pointers, or whatever? Kind of strange. If anybody knows why. And the strange thing is, I think they realize now that it's too big, but they say we cannot change it anymore, because if we change the size of the function object, then we change the ABI. And it will break all the old code, cannot combine this anymore. And this incompatibility also already bites us between libstandard C++ and libc++, because you cannot cross-use your C++ libraries with that. So you have to compile again, all with the same standard library. So one motivation to roll your own function implementation would be to make it smaller. But you don't have to do it your own. There are already implementations. There are quite a lot of them. And as I said, there are some possible extensions you want to use. And I want to present some of them. So the first one would be to use call qualifiers. So in our signature types, we can also encode something like no except or const. These are the call qualifiers. They are not like comparable to a normal type. So if you try to remove const, it will not remove it from the signature. These are different kinds of const. It's C++ after all. And what does happen if we would create a function 2 with this signature? Then the call operator of our function object will also be no except. So this might help to prevent your compiler from creating exception code in cases where it's not needed. And it would also mandate that to construct such a callable, such a function object, you have to have a callable that is also no except callable. And it would will also work for const and non-const and so on. So that's the first extension. The next one would be to have multiple overloads in one function object. Any idea when this comes in handy or useful? One useful thing is, for example, to visit a variant with that kind of function object. And then for different contents of the variant, you call different overloads on your function object. And if you, for example, have something like a network API, where you get different kinds of packages, then you have different handlers for these different commands, for example, and one command is shut down the system, one command is updated or log in the user, and then you have different overloads and can easily also extract some state objects that only exist once in this kind of function object. So example would be to have one callable with two overloads of the callable operator. And you can also create it by, for example, deriving from different lambdas, the overload pattern, basically. And then, yeah, depending on which type you give as an argument, you call different overloads. Okay, then more ideas. There's the moveonly, which is also implemented by function 2 and by C++23 standard. We'll have a look a bit more into detail how this works. Then there's the idea about non-owning function objects. So instead of owning the callable, we can also have like a pointer to the callable or a reference, depending how you see it. Then you manage the lifetime of the callable somewhere else and have just a reference. There were also a lot of proposals for the standard for that, but so far I think none got through. And yeah, then you could customize the small buffer behavior to tune your size depending on your needs. So if you have a task scheduler, you might say, okay, I'm expecting large tasks here, use a bigger function object, because we also have a queue where every node is allocated anyways, so why allocate twice if one allocation would be enough? And memory is, in this regard, cheap, that we don't use it, as long as we don't use it. Then there's also like polymorphic allocator support, might be thinkable. Also function 2 implements that. And we could also customize the empty handling. So instead of throwing an exception all the time, which is, for example, bad for embedded devices, where you would want to disable exceptions, you would like to have something like, if it's empty, then call my standard implementation or create a default implementation when it's possible. And if it's not possible, I can provide a standard implementation. For example, if you have a function that returns a reference, there's no way to default implement that. But if you return an int, you can default construct the int and return that. And there's also like an idea to make it const-expr usable. So far, standard function is not const-expr usable. I don't know if nobody got around to do it, but it seems also very difficult. So far, I couldn't come up with a solution for that. Yeah, we could also write an extension where we totally disable allocation and say, yeah, if my function object doesn't fit in this small buffer, then let's make just a compile error and avoid using heap for embedded systems, for example. And then one more thing I implemented and needed is a C API wrapper, where you say I have a function object and I have a C API, and the C API gets a void pointer and a void function pointer, and I want to make this work. So I want to extract these two C pointers out of my function object. So anybody else with extension or ideas? I think you can see there's a lot of possibilities, and as you see, like 4 are already implemented by function 2, and 1 is already implemented by C++23. So let's take a look at moveonly function, because there's also some other things to learn here. So the first thing, as the name suggests, moveonly function means we have a callable that has not to be copyable. For example, if you have a lambda that captures a unique pointer, this won't be copyable, because a unique pointer you cannot easily clone. So we have no copy support in it, that's by name. And there are some other interesting traits they got right now. So for example, they have the call qualifiers correct now. So you can have a const or no accept in your signature, and that also applies to your call operator of your function. And yeah, you can again construct it with any callable object, like data members, member function pointers, and so on. Still works. And it also supports the in-place construction. So the standard function, you can only give it a callable as a copy, and then as we implemented it, it moves it or copies it into its internal container. But moveonly function supports that you give it arguments and it constructs it on the heap or in the small object buffer directly. So there is some overhead that might be mitigated for that. And also they got rid of the runtime type information. So they're no longer target type or target. So if you need that use case, then it's not usable. But all the other features, I think, make it more usable than standard function in many use cases, because yeah, smaller surface, less function implementations. But that it's a different API also means it's incompatible to a standard function. So it's not like in place, you can change it and then it should work. There are differences. There are not many implementations so far. The implementations I have seen, they are not smaller. So if you compare the size between a standard function and the moveonly function, they're the same. They use the same amount of small buffer like you use in standard function. An interesting twist is, if you read the standard, they also changed the wording on this recommendation. They now only recommend that for small objects you do not allocate on the heap, but they do not say anything about member pointers or pointers anyway. So what is a small object is now totally implementation defined. Yeah. So that's all I have here. So let's summarize all the extension parts. For the whole talk, again, function signatures are types. That's the main thing you should take away here, because it's also useful in different scenarios. And standard function is very useful. It has its problems, as we said in the beginning already. So the world is bigger than standard C++. So you can use, for example, function 2, which implements a lot of extensions. And there's also the moveonly function now in C++ 23. So with that, again, I'm Andreas Reischuck. You find me on the internet. Use our company if you need help. Hire us if you need training, or work for us if you want to work for us. And we are located in Germany, Dresden. So if you want to work for us, we are 100% remote now. And speaking of Dresden, there's also the user group in Dresden. So far, we have no presentations this year, and we want to restart it next year. So we need presentations. If you have an idea, then speak to me. Deal is, if you speak, you also get a tour in Dresden if you come to us. If you speak remote, then you have to come extra to Dresden. Let's combine that. So we also do video recordings of all the talks. And if you don't like it, then we also don't publish it. So if you want to try speaking, you can also review the video and then say, no, let's not put it on YouTube if you don't feel comfortable. And the other thing, if you talk in Dresden, I will also drive to your user group and also give a talk there if you want to. And one final thing, my project is like all modern big companies now building other languages. I describe it as a big experiment, nothing to do with C++. Only the compiler is written in modern C++, because I like C++ best, and let's build it with the best language we have so far. But the idea is not to replace C++, but try different ideas how languages should evolve far beyond whatever exists today. So everything imaginable is possible. And if you have interest in languages, then speak to me as well. So hack more. So going deep in the standard function revealed a lot of facts. I hope you learned something. And that's so far the end of the talk. And now I'm open to questions. There's one in the back.
So I thought that std move-only functions was a renaming of the function ref, and function ref has the nice property that it's very small and it never allocates. But that seems not to be the case.
No, that's definitely not the case.
Is there anything I should be looking for if I'm looking for function ref other than function ref, obviously?
Yeah, take a look at any third-party library that you like. I have to say I looked for it and didn't find anything that was compelling to me, because it's not that easy to implement it correctly. And so far, I think that's also the reason why it's not in the standard yet. So as Nico said yesterday, we need more experience with these kinds of constructs. And then we have to standardize daily use stuff instead of inventing stuff for the library. And then afterwards realize runtime type information in a basic type like standard function might not be the best idea. There's one here in the front.
Just as a comment, specific question about function ref, I'd like to point out in Qt we have a private implementation of function ref. It's like one paper revision behind, I think, nowadays. But if you want to look for code and are happy with LGBL, look into Qt core private function ref.
Yes, one in the second row.
Why is standard function, why doesn't it support move-only callables by default? And why do we need a new type to support it?
We need a move-only function because the normal standard function mandates that it's copyable.
Yeah, I mean, why can't we just change the standard to say that, oh, no, but I mean, no. I mean, as far as I can tell, it would not break any kind of compatibility. As far as I can tell, that's why I'm asking the question, right?
Yeah, for example,
as I can see, if I'm not copying the standard function, then I should be able to pass a move-only callable, right?
No. Why? I can explain. The explanation is basically, how do you implement that? That's the part we skipped by using a shared pointer here. So how normally as you would implement it. So we had the interface, and our interface had only one function, one virtual function, that is call. And to implement something like copy or move, you have to add more virtual functions to that. One would be copy and one would be move, and there will also be something like destruct. So destruct is the destructor, but yeah, depending on your use case, you want to make it explicit. And and then you pay for it because there is a virtual method for that. And the virtual method has to be implemented because the virtual function pointer has to always exist. And because it has to exist, the object also has to be copyable. And if you make a move only, then the virtual function for copy would not exist. So the callable doesn't have to be copyable. You know? Okay. And in the actual implementations, they don't use virtual functions, but they use something similar. So thinking about virtual functions is correct or good enough here. So if you want to go further in this going deep, then we can talk offline, I guess. I didn't want to go much deeper than here, how it's actually implemented. More questions? If there are no more questions, then you get some questions. There's a bonus quiz. So, very simple questions. The question is, how big is the thing? What is printed here? We have one? More? Less? Different answer? It's always 23. No.
Did you say that the signature has no size?
Exactly. It doesn't compile. Someone who keeps up with me. Good. So someone learned something. And one interesting caveat about this, GCC has an option, permissive, and if you enable that, then you get 1. So 1 is also somehow a bit correct. But normally, in all the compilers with C++20, it won't compile. So next, same question. How big is that? Good question, yeah. But can you be more specific, even without knowing the platform?
4 or 8 bytes. 4 or 8 bytes, depending on the platform.
Yeah, it's just the size of the void pointer. It's just the pointer size. And it's 4 on 32-bit and 8 on 64. Correct. So now more. What's the size of this?
Now it depends on the compiler.
No, it's the compiler. No standard library involved here. So answer is correct so far, but yeah, it is. But what are the actual numbers here?
2 pointers, I think, for GCC, and I think 4 pointers for Microsoft.
No. Not exactly. So I measured it, and one thing is true on Clang and GCC, it's always 2 pointers. So, and on Visual Studio, it's 1 pointer. Exactly. Visual Studio has some curious special cases. If you have multiple inheritance involved in your class hierarchy, then it would be not 1 pointer, not 2 pointers, but 1.5 pointer, because they use 16-bit for the index. They assume you cannot derive from more than 65,000 classes, I guess. But the strange thing is, even though Microsoft has the smallest member function pointer, it has the biggest standard function object. That's strange. Okay, so let's learn one more thing. So to invoke this thing, you have to write this strange syntax. Everybody knows it? Okay. So then I want to show you one more trick to get around knowing all these kind of syntax, and also to prevent having to store 2 pointers for a member function. We just work around this with a lambda. So we define a signature that takes the object and the arguments from the member function, and we create a lambda and assign the lambda to the pointer. This works because our lambda doesn't capture anything, so it's basically a glorified function pointer. So it converts. And now, what's the size of the pointer? Exactly, it's 1 pointer always. It doesn't matter which platform we are, it doesn't matter how many classes we derive virtually or whatever, it's always 1 pointer. And To invoke it, we just have to call it. There's no special syntax about it. Okay. That's all for the quiz.